Hey CW Apes, Mr. Kennedy here with part 2 of your chapter 18 lecture notes on water everywhere. So in the first part, we were looking at like the hydrological cycle and water coming down from the sky and where it went. Well, we finished that by looking at how fast we're pumping water out of the ground in places like the Ogallala Aquifer. Well, the next area we're going to look at is how water can be diverted from one place to another and result in droughts. So kind of the unequitable distribution or use of water on a global scale. So a diversion is the transfer and subsequent maybe even storage of water for redistribution, right? That's what diversions do. China faces like a massive water crisis. South water, north diversion was first proposed by Mao Zedong in about 50 years ago. And the plan there was to build 3 canals to move water from the Yangtze River to northern China. The preliminary cost was about 400 billion yuan, about $62 billion in U.S. money. Incredibly expensive, but taking water from one part of the country and moving it to another. That's what a diversion is all about. This stuff goes on here in the United States as well, but here's another example. This is the Aral Sea. The Aral Sea was once a large inland, ocean, if you will, which supported a wealth of surrounding communities and fishing industry. Unfortunately, it has experienced an 80% decrease in volume due to diversion for agriculture. And nowadays, most of the Aral Sea, it's just an inland desert. All right. So diversions are serious problems when one community becomes more greedy than another and basically just siphons the water away. Rivers and streams. So rivers and streams, usually they're all about moving water from one place to the next in a natural setting. Precipitation that does not evaporate or infiltrate into the ground will run off the surface back towards the sea through rivers and streams. And we can actually measure how much this water is moving by measuring the discharge rate of a river or stream. The amount of water that passes a fixed point in a given amount of time period, usually expressed in cubic feet per second, is the discharge rate of a river. And when we think about like water moving around the country, there's an interesting fact when you look at our map. Like I've often asked questions like, why are some of the states shaped the way they are? I mean, if you look at these things, like they've got some pretty interesting kind of like architecture around them. And after doing a little bit of research, and if you do a little research on your own, you're going to find out that the majority of our states are shaped the way they are because of things like water, right? Like if we follow the Mississippi River all the way up from the Gulf of Mexico to its source, there's one state after another that literally clawed and fought to have borders with the Mississippi River, because back in the day, not only was it a water source for agriculture, but it was like the super highway for commerce. So like rivers and streams can play huge and important roles in society and in community. This is the biggest river closest to us here in California. It's the Sacramento River, and it taps into and is connected to the San Joaquin, which comes all the way down to our doorstep. The San Joaquin River used to be, at a time in history, broad and deep and big enough for us to literally sail ocean-going vessels from the Delta all the way to here and back. And it was a great connection point for commerce. It was also used for agriculture and, of course, for providing water for the surrounding community. There are tons of major rivers around the world that you should be familiar with. Some you might already know. Some of these names might be new. The biggest river in the world, that's the mighty Amazon River, right? No, not Amazon the shopping center that sends you all the stuff that gets dropped off on your doorstep. It's a river. And if you look at that, they have 175,000 cubic meters of water discharged every second from the Amazon River in through Brazil and Peru. I mean, that is a massive amount of water, right? So Mississippi is also on the list. Compare the Mississippi to the Amazon, and the Mississippi, I mean, it's almost a trickle, all right? But it's our biggest river here in the United States. Lakes and ponds. So bodies of water that ultimately are formed as rivers and streams find depressions and fill them up. Ponds are obviously smaller than lakes. Ponds are generally considered a small body of water, shallow enough for rooted plants to grow almost to the bottom. Lakes, on the other hand, these are large inland depressions that hold standing fresh water year-round, with depths ranging from a few meters to, somewhere in the neighborhood of 1,500 meters. Both ponds and lakes will eventually fill in with sediment through the process of eutrophication and become like, meadows, right? Dry land, okay? But that's going to take a lot of time, to fill in a lake that's 1,500 meters deep compared to a pond that might only be a few feet. Wetlands. Wetlands play a vital role in the hydrological cycle. In our state, most of the wetlands that we once enjoyed along our coasts and other bodies of water are gone. Wetlands themselves are, lush plant growth areas that stabilize soil. They retard surface runoff. They allow for aquifer infiltration. They provide habitat for countless aquatic species. They're kind of this really amazing buffer zone between fresh and salt water. Probably the ones that you're most familiar with are the estuaries that abut up to the ocean in places like the Central Coast, right? Kind of like the breadbasket, if you will, of biodiversity along the coastline. Estuaries are places where fresh and salt water mix, and they support vast amounts of life, but they're also disappearing at an alarming rate. Aside from biodiversity, another really great thing that you need to remember that wetlands do for us is they act as a natural filter and buffer against storms. So like when hurricanes hit, when there's floods, things like that, the wetlands can literally absorb storm surge and protect us from those things. They're really, really important. The sad part is that, well, for lack of a better way to put it, as our numbers go up, our population increases, wetlands have sometimes been looked at as prime real estate. They're drained and houses are built, roads are cut through them, all kinds of stuff like that. Even Disneyland in Florida sits on what was once wetlands, okay? All right, atmosphere. So let's look at the atmosphere. How does the atmosphere play a role in this whole hydrological cycle? Well, the atmosphere is a pretty small water compartment compared to the ocean itself. It really only contains like 0.001% of the total water supply that's out there. Has probably the most rapid turnover rate, but provides the mechanism for distributing water over land masses. So that's why we got to talk about it. Water that moves over land masses will eventually become water that's available for us to use. That forms our renewable water sources. Renewable water supplies or water sources are made up of surface runoff plus infiltration into accessible freshwater aquifers. And about 2/3 of water carried in rivers and streams annually occurs in seasonal floods, too large or violent to be stored effectively by humans. So we can't really rely on the 100-year flood to supply us with enough water to make it through the next 100 years. We need to harness the water as it comes in small quantities, right? So readily accessible renewable supplies of water are really only about 400,000 gallons per person per year, which I know sounds like a lot. But then if you start thinking about all the ways that you use water, you'll realize that most of us are using much more than that, okay? Many countries suffer from water scarcity. The United Nations considers 264,000 gallons per person per year to be the minimum necessary to meet human needs. Okay, water stress occurs when humans and ecosystem needs exceed the renewable water supplies, resulting in competition. Periodic droughts create severe regional water shortages in semi-arid zones where moisture availability is the critical factor in plant and animal distributions. The effects, folks, on water supplies may be the most serious consequence of global climate change. Here's some examples. When you talk about the availability of fresh water and its scarcity, just go back to that graph that I showed you at the beginning of this in our first video, and you'll see just how little water is available for us. Thinking about what we use our water for and where it goes, let's look at this. Okay, human water use has been increasing about twice as fast as population growth over the past century. But impact does vary by location. Canada withdraws less than 1% of its renewable supply a year. And I know what you're thinking, like, what are the Canadians doing that we're not? Well, first of all, they're probably, one of those countries that gets that like unfair share of water. So they're getting a lot more water than probably what we are here in the lower 48. In Israel, Libya, and Yemen, groundwater and surface water withdrawals equal more than 100% of the renewable supply. And so they're literally out there mining for water, and it's not sustainable. The U.S. currently uses 20% of renewable water per year. So we're doing okay for now. All right. Where is it going? Well, withdrawal and consumption look like this. When you withdraw water, this is the total amount of water removed from a water body, and then consumption, this is the loss of water due to evaporation, absorption, and contamination. The biggest and greatest consumer of water is ag. And I know what you're thinking. We have to have agriculture to raise food so that we can eat. I know, right? And as our population goes up, there's more pressure on agriculture to produce more food, which means we could be just pulling more and more water out of the ground. Worldwide, agriculture claims about 70% of the total water withdrawal and 85% of its consumption. Again, the Aral Sea is a great example of this. Once the fourth largest inland body of water in the world, it's now lost 90% of its volume since 1975 because water was diverted for irrigation of rice and cotton crops. And all the commercial fisheries have been lost. Again, here's what it looks like from then to now. Water use in the U.S., if you break it down and look at these percentages, it really just comes down to how much rainwater you get and, to how much you're going to have to pump out of the ground. There were times where maybe, throughout the course of a year or two, we got enough rain to support crop growth without us really having to pump water out of the ground. But that's not necessarily the case anymore. Pretty much everywhere you go, all crops are going to be raised as a result of some sort of groundwater, extraction. And there's just no way to get around it. Okay. Irrigation accounts for 70% of water withdrawal. And irrigation can be both efficient and inefficient. It just depends on how it's being done, right? Drip irrigation that delivers small quantities of water that's allowed to soak into the soil right at the base of the plant is way more efficient than just spraying it off into the air. But there are still plenty of places that just spray it off into the air because that's cheap and easy. Flood or furrow irrigation was something that has been, around literally for centuries. So basically, you just plant your crops in rows with little furrows next to them. You flood the field and you just let the water sink in. Half of the water that you use in this way can be lost through evaporation. This is probably one of the worst ways to irrigate, right up there with spraying it into the air. Flood irrigation used to remove salts from the field, but now salt contaminates the streams. So what are you going to do with the salts? Sprinklers, like I said, they have a high rate of evaporation, and drip irrigation is the most efficient. Unfortunately, it's used only in 1% of the world's croplands. All right, domestic and industrial water use is the next big culprit to talk about, like where our water's going. Worldwide domestic water use accounts for 6% of water withdrawals, only about 10% of consumption. But where sewage treatment is unavailable, water is degraded. So, you got to have sewage treatment to protect your water. Most developed countries do, the developing ones don't. Industry accounts for 20% of global freshwater withdrawals, ranging from 5 to 70% in various locations based on the amount of industry. Small proportions of that water is consumed, but degradation is a huge problem because industry is using that water like as a solvent, and water will pick up anything that it touches and take it with it. Typical household use. Let's talk about us, okay? So if you look at this, number one culprit of household water use is the good old commode, right? Every time you flush. Like the easiest way for you to have a direct impact on how much water you use is to use low flow toilets, right? That'll reduce your consumption dramatically. The next thing you got to look at is things like showers and, running the faucet while you brush your teeth, and how long do your sprinklers run? All of those things impact the typical household water use in the United States today. Now, if we don't do something about like pumping water and pulling water out of the ground faster than it can be replenished, we're bound to experience freshwater shortages. The UN estimates that 1 billion people lack access to safe drinking water. 2.6 billion lack acceptable sanitation, resulting in millions of water-related illnesses and deaths. In many countries, it is not access to water that's the problem. It's access to clean water that's the problem. If you don't have wastewater treatment plants, if you have agriculture with fertilizers and pesticides, or even just open dumps that's near a water source, right, that's going to contaminate your water. A single drop of motor oil can contaminate hundreds of gallons of water and get it to the point where we can't drink it. By 2025, the UN estimates that 2/3 of the world's population will be living in water-stressed countries, right? So that's a terrible tragedy. Many lack access to clean water. More than 2/3 of the world population lack indoor plumbing and must fetch their water from outside their home. Where water is available in the home, it may be expensive. In Lima, Peru, a typical poor family uses 1/6 as much water as a typical middle-class family in the U.S., and they pay 3 times as much for the water. And then they have to boil that water before they can even drink it, right? We need to make sure that we care for our water supply. In a place like California, parts of the state have more water than others, and as a result, we move and store water as much as possible to help increase water supplies for places that, maybe are experiencing water stress. There are 1,300 reservoirs in California and 1,400 dams in California to store water. There are thousands of miles of canals, aqueducts, and pipes to distribute water up and down the state. This is all expensive infrastructure, and if you live in a developing world, oftentimes your government can't afford this type of infrastructure and technology. So this water stress goes on. So outside of taking care of what you get, what else can we do? Sometimes people talk about increasing water supplies by seeding the clouds with condensation nucleus. The jury's kind of out in the effectiveness of something like this, but I suppose maybe someday in the future, like there will be a company that makes a living doing just this. Another thing that's often talked about is desalination plants. Like, hey, instead of pumping it out of the ground, let's go after the water that's in the ocean and we'll suck that in, take the salt out, and then we'll put fresh water into circulation from that. I'm here to tell you that this is probably one of the most horribly inefficient processes that there is on the planet. I've got another video that I'll show you that explains exactly why. So 3 to 4 times more expensive than most other sources. Like desalination is not something that is going to come cheap or something that's going to produce enough water in mass like to support huge communities. All right, ladies and gents, I'm going to take a break right here. This is the end of part 2 of your Chapter 18 notes on water. When we come back, we're going to wrap this all up and look at other things that we can do to protect and preserve our water resources. I'm Mr. Kennedy, and I'll see you in just a minute.